Today we are going to discuss about the hybridization. This is the electron configuration of carbon. In its ground state, the carbon has 2 electrons in the 2s orbital and 2 unpaired electrons in the 2p orbitals. If carbon only used these 2 unpaired electrons in bonding, it would only form 2 covalent bonds. But we know carbon can form 4 bonds. So, how does it get from 2 to 4? The answer is the excitation of carbon. During the excitation, one electron from 2s orbital gets excited to the empty 2p orbitals, resulting in 4 unpaired electrons that facilitates 4 covalent bonds. But the s and p orbitals have different shapes and different energies. Now we have a problem. Why are all these bonds identical in a molecule like methane? The answer is the hybridization. What is hybridization? Hybridization isn't just a fancy word. It is a mathematical mixing. Just imagine you have a bucket of white paint and 3 buckets of blue paints. If you mix them together, you don't have separately white and blue anymore. Now you have 4 buckets of light blue paint. Similarly, when S and P orbitals are mixed, you don't have S character and P character anymore. You will have identical 4 hybrid orbitals. They are called sp3 hybrid orbitals. The mixing of orbital is called sp3 hybridization. Then what happened to the S and P characters? sp3 hybrid orbital has 25% of the S character and the 75% of the P character. All 4 hybrid orbitals have the identical energy, which is intermediate between original S orbital and the P orbitals. What is the shape of hybrid orbital? A hybrid orbital has a long, elongated lobe and one tiny nub. What is the spatial arrangement of 4 hybrid orbitals? The larger lobe of sp3 hybrid orbitals extended towards the 4 corner of regular tetrahedron with 109.5 angle. How is a carbon-hydrogen bond formed in a methane? Then sp3 hybrid orbital of carbon overlaps with the 1s orbital of hydrogen to form CH bond. This is the molecular orbital picture of methane. What is the use of hybridization concept? Actually, it explains the molecular geometry. The tetrahedral molecular geometry is very well explained by the sp3 hybridization. sp2 hybridization is suggested in order to explain the trigonal planar molecular geometry. In this hybridization, 1s orbital and 2p orbitals get combined to form 3 identical sp2 hybrid orbitals. These hybrid orbitals lie on a same plane. Larger lobes are extended towards 3 corners of a triangle. This allows a trigonal planar molecular geometry. sp hybridization is suggested to explain the linear molecular geometry. In this hybridization, 1s orbital and 1p orbital combine to form 2 hybrid orbitals. These hybrid orbitals are oriented linearly at 180 degrees angle to each other with 2 larger lobes pointing in opposite direction along a single axis. This allows a linear molecular geometry. You know, students, electron pair geometry is related to the number of VSEPR pairs around the central atom. So, we can predict the hybridization of a central atom by considering the number of VSEPR units. Look at this table. Number of pairs 2, electron geometry linear, and the hybridization become sp. And if there are 3 pairs, And geometry is trigonal planar, hybridization become sp2. And if there are 4 pairs and geometry is tetrahedral and hybridization is sp3. The hybridization of the beryllium in beryllium chloride is sp because around the beryllium there are 2 Wesp pairs. Can you guess the hybridization of boron in BF3? It is sp2. Around each carbon in ethene there are 3 sigma bonds. Therefore, the hybridization of each carbon become sp2. There are 2 sigma bonds around each carbon atoms. Therefore, the hybridization of carbon is sp. Dear student, now I am going to conclude today's discussion. If you have any inquiry, please comment. Okay, students, thank you for watching.